Okay, we have in this module we have looked at the unsteady flows, particularly focusing on our attention to the shock tube, and that is a very good template problem to understand 1D unsteady gas dynamic flows, and we went through in detail solving all parts of flow features that are present in a shock tube. Now let us just do few numericals to get these concepts little more clear. So let us do some numericals. So consider this example, numerical example 1. Consider a pipe in which air at 300 Kelvin and 1.5 into 10 power 3 Newton per meter square Pascal flows uniformly with a speed of 150 meter per second. The end of the pipe is suddenly closed by a valve and a shock wave is propagated back into the pipe. Compute the speed of the wave and the pressure and temperature of the air which has been brought to rest. So this problem, if you look at it, so you know that the initial condition is that you have a flow that is going at 150 meter per second. In originally it is a open tube. Okay, so 150 meter per second, and T1 is 300 Kelvin and P1 is 1.5 10 power 3 Pascal. Then suddenly this valve or this portion is closed by a valve. It is sudden. This is important. This has happened suddenly. So instantaneously the velocity at this wall should be going to 0. So you should get u is equal to 0 at the wall. Now this you should sort of connect it to whatever we had discussed in our classes on the unsteady flows and moving shock waves. When is this accomplished? This kind of motion can be accomplished when you have to suddenly bring a flow to rest, which is a high speed flow. 150 meters per second is quite a good speed. This is done by a shock. This is very similar to the reflected shock problem of the shock tube, where you have the incident shock. Behind the incident shock there is mass motion of the gas. This mass motion is not insignificant. They have relatively good velocities, and on striking the end wall of the shock tube, immediately the velocity has to go to 0. If this has to be accomplished, then a reflected shock is formed, or a shock wave is formed, which moves into the gas, which moves in this case it moves into the pipe with a speed Wr, and this is u1, and we can say this is u2. u2 is 0 in the fixed laboratory frame of reference. How do you analyze this problem? It is a moving shock problem, and all we have to do is change the frame of reference. From laboratory frame you move on to the shock. If you do that, you will impose a velocity, equivalent velocity Wr here. Now u1 is also in the same direction, so the relative velocity here is Wr plus u1, and relative velocity here is Wr, and now you can apply stationary equations, stationary gas equations. So if I say in the stationary frame of reference, what is m1? m1 is Wr plus u1 by a1 is m1. Now also consider what is u1 by u2. Okay, u1 by u2 is rho 2 by rho 1 is Wr plus u1 by Wr is equal to rho 2 by rho 1 of the shock, which is for the shock with Mach number m1. This is well known. m1 square by 1 plus m1 square. Okay. Now can we express, we know that this is the equation for m1, can we express WR in terms of m1? You can write it, WR is m1 a1 minus u1. Okay, so once this is known, so you have this and you have this relation, so we can put them together. So we will put it together and write them together. So you have gamma plus 1 by 2 m1 square divided by 1 plus is equal to u1 plus wr by u1 wr, which is u1 plus m1 minus u1 divided by wr is m1 a1 minus u1. So here these terms go off, so you get m1 a1 and 1 m1 can be cancelled off with this 2 here. So now you get a gamma plus 1 by 2 m1 multiplied by m1 a1 minus u1 equal to 1 plus gamma minus 1 by 2 m1 square multiplied by a1, because a1 is still remaining here. So now we can write this, so gamma plus 1 by 2 m1 square a1 minus gamma plus 1 by 2 m1 u1 is equal to a1 plus gamma minus 1 by 2 m1 square a1. So now you are approaching a quadratic quadratic equation, algebraic equation. So you can take this here, so this side, so gamma plus 1 by 2 minus gamma plus 1 by 2 m1 square, this is how it looks. So a1 minus gamma plus 1 by 2 u1 m1 a1 equal to 0. So this is 2 by 2 is equal to 1. So get a1 m1 square minus gamma plus 1 by 2 u1 m1 minus a1 equal to 0. Roots of this, so m1 is equal to gamma plus 1 by 2 u1 plus square root of gamma plus 1 by 2 u1 whole square plus 4 a1 square divided by 2 a1. This is gamma plus 1 by 2 u1 by a1, so gamma plus 1 by 4 rather, plus you can take 2 a1 inside, so you will get gamma plus 1 by 4 u1 by a1 whole square plus 2 a1 if you take inside, it will be 4 a1 square, so this is plus 1. You will take the positive term because if you take negative 1, this will be greater than gamma plus 1 by 4 u1 by a1, so it will have a negative value, so that is not possible. So you take the positive value. Now in this we know u1 is known 150 meter per second, a1 is square root of gamma r t1 for air 1.4 287 multiplied by 300. This value is known, it is around it should be 347, coming close to 347, and you can solve this now. You can substitute these values here and find out what is m1. M1 it turns out to be 1.29. So, what is the wave speed WR? It is m1 a1 minus u1, and you can substitute the values again, and the wave speed is 297.63 meter per second. So, you should understand that Mach number for the reflected wave what we consider is actually WR plus U1 by A1, not WR by A1. So, please bear that in mind when you have a primary shock moving into a quiescent medium. So, here this is the primary shock moving into a quiescent medium, A1 and U1 is 0. So, here MS, if you consider MS is W by A1, because U1 is 0 here reflected. I mean, if you transform the coordinates also you will get it, but if you consider a reflected wave going in to a region where there is already a certain velocity U1 and this is WR, then the speed of the Mach number for that particular wave is WR plus U1 by A1. This has to be borne in mind. It is you have to be careful with this. So, we still have the values for pressure and temperature behind the shock. So, that is once you know M1, it is straightforward. You just have to look at either the tables or look at a calculator and find out what is P2 by P1. We know M1 is 1.29, P2 by P1 is 1.775. So, consequence P2 is 2.66 into 10 power 5 pascals. Similarly, T2 by T1 is 1.185. You can put this value and you will get T2 as 355.5 Kelvin. So, you can do this methods straightforward. So, now once this is known, now let us move to the. So, this is a good example of shock wave reflection from the end, and it is applied to a problem where suddenly the valve is brought to close and the flow is brought to rest. So, those kind of problems also have relations to the shock tube problem. So, the second example is calculate the pressure required in the driver section of a shock tube to produce a shock Mach number 3 in the driven section which contains air at an initial temperature of 300 Kelvin and pressure of 0.01 atmosphere. So, it is low pressure. You can draw the schematic here, and here you know T1 is 300 Kelvin and P1 is 0.01 atmosphere. We do not know what is P4, we have to find P4. Driver gas is air at 300 Kelvin. So, it is the same gas, T4 is 300 and gamma 4 is equal to gamma 1, the same gas. If flow behind the shock wave is directly used without shock reflection for a short duration wind tunnel. So, this is a case where you are taking the shock tube and at the end of it you are attaching a wind tunnel. So, this combination is known as shock tunnel. We will discuss this in coming classes, but principle almost all of it you are for the shock tube is already known. So, after the diaphragm ruptures you have a shock wave and you have a contact surface. There is a slug of gas between this having high pressures P2 T2, and this slug of gas is then utilized for the wind tunnel. You may use this by having a shock reflection back and increasing the pressures to P5 T5, and that forms the reservoir section for the wind tunnel, or you can use just the P2 T2, and what is said here is there is no shock reflection, that means directly we are using P2 T2. Given that the test section is 8 meters away, so the distance between the diaphragm station and the test section is 8 meters, and contact surface is the disturbance which limits the testing time. So, if you draw the XT diagrams which we have been drawing for some time now in the previous classes, we saw that there is a shock discontinuity, there is an contact surface discontinuity, and there are expansion fans. So, essentially this test gas between the shock and the contact surface is the gas that is used for any kind of experiments or aerodynamic testing, but you could get other effects, like if you allow this to run for longer time, the expansion fans can reflect off the end wall and come and make the flow non-uniform here. Essentially that ends the test time, or the other case is that the contact surface passes through the test section. Once that is done, again you get all non-uniform flows beyond the contact surface. These are the two cases. So, here it says it is the contact surface that is limiting the test time. So, the test time is limited by this difference between the shock and the contact surface. So, what do we need to calculate? Static temperature and pressure behind the shock, stagnation total temperature and pressure, test time available, the angle of the Mach line in the flow behind the shock. Okay. So, first point is calculate the pressure required in the driver section. So, what is P4? So, directly you can apply the equations P4 by P1 2 gamma 1 m1 square gamma 1 minus 1 by gamma 1 plus 1. So, this is direct from, you can use the textbooks or you can use the notes, and so this formula, if you put, we know m1 is Mach 3, Mach number is 3, so m1 is 3, and a1 by a4 both are a1 equal to a4 equal to square root of gamma r t, which is 1.4 multiplied by 287 multiplied by 300. Okay. So, gamma 4 equal to gamma 1, we know this, and if you substitute this you can get P4 by P1 directly, it is 632.627. So, you can see to produce a Mach 3 flow of Mach 3 shock wave in a shock tube, you need 600 times the pressure in the driver driven section. So, that is why you generally keep high pressure as well as low pressure. So, you evacuate the section which is driven section is kept at low pressures, in this case 0.01 atmospheres. Otherwise, if it was at 1 atmosphere, you can imagine you need to give 632 atmospheres here, but you can manage a fairly strong shock by using low pressures here, and then the pressure at P4 is only 6.326, which is 6.33 bar. Okay, so that gives you the pressure that pressure ratio across the shock tube that needs to be provided so that you get the shock. And once the shock is formed, what is the stagnation pressure and the stagnation temperature. So for the flow, so that is P02 and T02, these are the conditions. So for that we need first P2 by P1 and T2 by T1. This you can get given that it is a Mach 3 flow, 10.33, and T2 by T1 is 2.679. So P2 is 0.1033 atmospheres, while T2 is 803.7 Kelvin. Now stagnation pressure, if you have to calculate for the region 2, you have to do the calculation for P02 is P2 multiplied by 1 plus gamma minus 1 by 2 M2 square gamma by gamma minus 1. What is M2? M2 is U2 by A2. Now you have to calculate U2. Okay, so you can you know MS, you know P2 by P1, you can directly use the relations of what is U2 by A2 in terms of A1 by gamma and the various ones, that you can also use that, or you can also go slightly from the first principles, that U2 is Ws multiplied by 1 minus rho 1 by rho 2, and if you know P2 by P1 and T2 by T1, you can calculate rho 1 by rho 2, and rho 1 by rho 2 turns out to be 0.2593, and Ws is nothing but M1 multiplied by A1. So from this you can get U2. U2 is U2 turns out to be 771.488 meter per second. So it is not small, it is very good velocity, but A2 is also large, therefore you get M2 is 1.3576. okay, so this is M2. So correspondingly, now once you know M2, M2 is U2 by A2, A2 is square root of gamma r T2. Okay, so now P02 and T02 can be found out. So P02 is 0.3098 atmospheres and T02 is 1099.95 Kelvin. So you see it is quite high temperature, approaching 1100 Kelvin. Now what is given is that the contact surface is the one which limits the test time, and if you draw the xt diagram, the shock wave passes right way and contact surface is here, and the test section is 8 meters. So this difference in time is the test time basically. So this is the difference in time, or delta t, which is the test time. Okay, so this is control contact surface, this is shock. Okay, so how do you calculate this? Is the same distance. So what is delta t for the same distance? The contact surface takes the time 8 divided by U2, speed of the contact surface, minus speed of shock 8 by W. U2 and W both are known, so you get delta t as 2.688 minus 3 seconds. So, you can see this is quite small, 2.688 milliseconds. Uh, but these facilities are often used for high temperature flows and high hypersonic flows, high enthalpy flows, and test times there are quite short, but the instrumentation is also made similarly, it is made advanced, and people get a lot of useful results from such facilities. What is the Mach angle of Mach line in the M2 flow? Nu is sine inverse 1 by M2. This turns out to be 47.44 degrees. Okay, so that solves this problem. So there are two problems we solved. One, the first one was the application of the unsteady principles that we had done towards a problem where there is a high speed flow in a pipe and suddenly a valve is closed. Then what happens, and how do we calculate quantities there. The second one was a template shock tube problem, where we know what is the shock Mach number required, and we calculate various quantities like what is the pressure ratio that needs to be provided, so that we can achieve that shock Mach number, and what's the properties of the slug of gas which is usually used for any applications, including in wind tunnels. So with this we come to a close on unsteady flows, and the next module we will be looking at moving from 1D equations, we were all in the 1D framework, to 2D framework, and look at shock waves and expansions in 2D framework. So that is when you go to 2D framework, the shock waves become at an angle to the flow. This is known as oblique waves. So what is normal shock is actually a special form of oblique shock, where the angle is normal to the flow, but at any other angle you get an oblique shock, and we will look at oblique shocks and the counterpart which will expand the flow. Shock waves compress the flow, they are expansion waves, and Prandtl-Meyer expansion waves. So we will see at that in the next module.